Here we are downloading the required libraries to R and running a test sample plot from 2007, then we move on to our example under discussion. The power law you're working with in the context of daily returns for the QQQ ETF offers insight into the relationship between volatility and time. A power law describes a functional relationship where one quantity varies as a power of another. In this case, you're looking at how volatility changes with time, specifically on a logarithmic scale. Interpretation of the power law. Log volatility versus log time. You're plotting the logarithm of volatility against the logarithm of time, which reveals a linear relationship between these two variables. This is indicative of a power law scaling, where volatility increases over time in a predictable manner according to a power law exponent. Slope, 0.4767. The slope of the log-log plot, 0.4767, represents the power law exponent. A slope of less than 1 suggests that volatility grows over time, but at a decelerating rate. In other words, the rate at which volatility increases is slowing down as time progresses. Intercept, 4.225. The intercept is a scaling constant that shifts the entire curve up or down. This value, around 3.17, tells you where the fitted line crosses the y-axis in the log-log plot, essentially giving you the baseline volatility at small time intervals, or when time approaches 1 on the log scale. We are looking at a scaling lower plot. What a scaling law is basically, Benoit Mandelbrot suggested that, in his chaos theory. When he originally looked at cotton prices, he found that the fundamental law of the efficient market and the subsequent pricing and normal distribution and so on did not actually fit the data accurately. And this is borne out if you actually look at the SP500 histogram of returns, not the actual prices, but of the returns, and the QQI and even the IWM. The QQQ is a proxy for the NASDAQ IWM as a proxy for the Russell. If you do the original, either one, the ETFs, or the original, you will find that they are approximately better fitted by a T distribution, with between 3 and 5 degrees of freedom. Now, a normal distribution doesn't kick in with a T distribution till at least 30 degrees of freedom. 20 to 30, but generally 30 to 100. So, yeah, it's way off being normally distributed. There are as many tests you can do for distributions, because the underlying data actually changes. The basis of the intercept changes a bit now and again. Maybe. The slope will change occasionally, but not too much. And for this one, I did the QQQ as a proxy for the NASDAQ, fitting capital asset pricing model beta, and alphas, which is incidentally fairly really inaccurate. The volatility is never constant, which is an assumption of normal distributions. The means are not a constant. Basically, the whole concept of modern finance is flawed, as Mandelbrot said. Anyway, I've got workings here, and I'll go through them to describe. However, you'll have to remember that I haven't updated the actual results because, as I said, when I do them every day, they change slightly. You'll get the idea from the data, how you do it, what you do. But the power of power. Form is of the form. Y equals, or the slope equals, or the dependent variable equals K, which is a constant times. X, which is the independent variable to the power of alpha,